Hello everybody, myself Prashant Mukhopadhyay, faculty member, Electrical Engineering Department, Greater Kolkata College of Engineering and Management. So in the electrical machine 2 class, actually in the last class we are discussing about the induction motor speed control by changing number of stator poles. So in this class we have discussed there are three methods by which the stator poles can be changed to impart the speed control of the induction motor, and we have discussed consequent poles method. Now today we will discuss multiple stator winding method, and later on pole amplitude modulation methods and so on. Actually, multiple stator winding method is a method where instead of one winding, two separate stator windings are placed in the stator core. The windings are placed in the stator slots only, but are electrically isolated from each other. They are placed, definitely these windings are placed in the stator slots, but they are electrically isolated. And each winding is divided into two coils to which pole changing with consequent poles facility is provided. So by giving supply to one of the two windings and using switching arrangement, two speeds can be achieved. So same is true for other stator windings. So in all four different speeds can be obtained. So this is not a very useful method nowadays. It has certain limitations also, and it can be applied only squirrel cage motors. Smooth speed control is not possible. Only step changes in speed are possible. Two different stator windings are required to be wound, which increases the cost of the motor, and definitely from the design point of view it is complicated. So these are the very big limitations because it is limited to only squirrel cage motors on application wide. Smooth speed control is not possible. Only step changes is possible in speed control. And since two different stator windings are required to be wound, which increases the cost of the motors, so this is a very vital point. And of course, if we think over the design point of view, so this method is very much complicated. So that's all about multiple stator winding methods. So now we'll discuss the pole amplitude modulations method. Basically, in this method, speed control of three-phase induction motor, the original sinusoidal MMF wave is modulated by another sinusoidal MMF wave having a different number of poles. Okay, so actually this is the main theme of this pole amplitude modulation method, where main MMF wave or original MMF wave which is sinusoidal in nature, so is modulated by another sinusoidal MMF having a different number of poles. Okay, so suppose F1 theta be the original MMF wave of induction motor, which speed is to be controlled. So and F2 theta this is the modulation MMF wave. So suppose P1 be the number of poles of the induction motor whose speed is to be controlled, and P2 be the number of poles of the modulation wave. So that can be written F1 theta equal to F1, that is the magnitude of the sine P1 theta by 2, and F2 theta equal to F2 sine P2 theta by 2. So after modulation, resultant MMF wave will be like this. If a resultant MMF is FR theta, so it will be a product of F1, F2 sine P1 theta by 2 and sine P2 theta by 2. Now if we this is the resultant MMF wave. Now it can be written applying our trigonometrical formula of 2 sin A sin B to cos of say difference by half minus cos of say sum by half. So sum by 2. So actually if we put this formula here, so this resultant MMF wave will be F1 F2 cos P1 minus P2 theta by 2 minus cos P1 plus P2 theta by 2 whole by 2. So this shows that the resultant MMF wave will have two different number of poles. One P11, which is the difference of the two poles, original MMF wave and say modulation wave, and P12, which is the summation of these two, actually P1 plus P2. So therefore, by changing the number of poles, we can easily change the speed of the three-phase induction motor. So in details, it can be discussed in many ways. So we are not going for total discussions. We are just talking about the methodology, how it can be done. So this is the say in a nutshell, the pulse amplitude modulation method, by which actually we are getting two different number of poles. So one is the original and modulation wave pole difference, and another is the original and the modulation wave number of poles summation. So therefore, by changing the number of poles, we can easily change the speed of a three-phase induction motor. So that is say pulse pole amplitude modulation method. So next we'll discuss say rotor rheostat control. So as we know, from the equation of the torque of a three-phase induction motor, the expression is torque is proportional to S E2 square R2 by R2 square plus SX2 whole square. So you all know that this is the torque actually, output torque, and this is actually this is the slip. E2 is the induced EMF of the rotor windings, and R2 is the rotor winding resistance, and SX2 is the say rotor winding reactance at slip S. So if we consider for low slip region, so if S is very low, in that case SX2 whole square is very less than this R2, and this can be neglected. For constant supply voltage E2, because E2 is directly proportional to a supply voltage, so we can write this is a constant supply because E2 is also constant. So therefore, we can write this equation can be modified as T proportional to H R2 by R2 square. So that gives you say S is proportional to R2. So from these equations, it is find there's the rotor resistance. If we increase this rotor resistance, torque produced will be decreased. Okay. So, but when the load on the motor is the same, the motor has to supply the same torque as the load demands. So the motor reacts by increasing its slip to compensate for the decrease in torque due to R2, and maintains the load torque constant. So this is evident. This is reflects from these equations when is for low slip, this torque is reduced at say increase R2. So as a result, to maintain the load on the motor is at same load condition. So motor has to supply the same torque as the load demand. So what will happen? So as a result, the speed will be sacrificed. So the motor reacts by increasing its slips to compensate for decrease in torque due to R2, and maintains the torque load torque constant. So as a result, so due to this additional rotor resistance, motor slip increases, that is speed of the motor decreases. Okay, so this is the arrangement of rotor resistance control speed control method. So this is the induction motor. This is the stator part, stator winding, where 3-phase supply is given, and this is the slip rings from where starting rheostat and speed control are connected to this slip ring to the rotor circuit, and as a result rotor resistance can be changed or increased, and by this method, so we can for the same load condition, torque will be decreased and the speed will be decreased, and so as a result slip will be motor slip also increases, that is the speed of the motor decreases. So what is the advantage of this method? So actually advantage, definitely some advantages are there. By increasing the rotor resistance to speeds below normal value can be achieved, and the starting torque of the motor increases proportional to rotor resistance. Okay, so because you know this again, if you go back to this equations, you will come to the point that these are the applications, but advantages. But what are the disadvantages? There definitely some disadvantages are there. Large speed changes are not possible because this is because for large speed change, the large resistance is required to be introduced in the rotor, which causes large rotor copper loss to reduce the efficiency. That's a very big problem. See, if you want to limit the speed change within a very low limit, then it can be okay. So, but if you want to get large speed change, that means the rotor resistance, external resistance will be large when it is be introduced or included in the rotor circuits, and as a result, so rotor copper loss will also increase. Whenever the loss is increased, the motor efficiency will be decreased. So this is the this reduces the efficiency. So that's why this method cannot be used for again this method cannot be used for squirrel cage induction motor, because by construction wise squirrel cage induction motor, the rotor are short circuited, and there is no provisions for the inclusion of external resistance in the rotor circuit. So this is not possible to apply this method in the squirrel cage induction motor. And another thing is that the speeds above the normal values cannot be obtained. So it is always, the torque is proportional to S by R2. So that means always it will be reduced, speed will be reduced from the normal value. It cannot be enhanced, okay, from the normal value. So, and another thing, large power losses occur due to large I-square loss, and as a result, so I told you that efficiency will be reduced, and sufficient since large losses means large heat production. So sufficient cooling arrangements are required, which make the external rheostat bulky and expensive. And I have already told you that due to large power losses, efficiency is low. So these are the say methods which can be applied to say speed control. So one thing by stator pole changing methods, either consequent pole changing or multiple stator winding, and then pole amplitude modulations method by say another auxiliary MMF modulation wave, okay, and as a result pole can be changed. Resultant pole will be either the some difference of the original MMF wave poles and the modulation wave poles, or it is maybe the summations, okay. And another thing is the rotor resistance control method, as I told you. So this is rotor resistance control, which is possible only for slip ring or wound rotor induction motors, and since this no provision is there for the inclusion or for external resistance in the rotor circuit, so it is not possible for the squirrel cage induction motor, and due to large rotor resistance, losses will be more and efficiency will be reduced. So this is speed can be controlled below or the up. So we have discussed the rotor rheostat control, and we have also discussed its limitations, advantages also. And I told you this since due to the introduction of the rotor resistance in the external resistance, so copper loss in the rotor circuit is more, and as a result the efficiency of the motor will be decreased. And not only that, large speed control is not possible in this method. Only speed can be controlled so below the normal speed or rated speed. And now we'll discuss another method, that is by operating two motors in concatenations or cascade or tandem operations actually. So basically in this method two induction motors are mounted on the same shaft. One of the two motors must be slip-ring types, and which is called the main motor, and the second motor is called the auxiliary motor, and this motor may be slip-ring or may not be. It can be a squirrel cage induction motor also. So these two motors actually connected on the mounted on the same shaft, and that's why it is called the cascade connection or concatenation connection or tandem operations. So an arrangement is shown here. This is the main motor and this is the auxiliary motor. So both are connected on the same, mounted on the same shaft. This motor here it is shown as a slip-ring motor, but it can be a squirrel cage also. So stator of this main motor is connected to the three-phase supply, okay, and the supply of the auxiliary motor is derived from the rotor sides of the from slip-ring to connected to the stator. That is, it is the slip frequency power is being fed to the stator winding of the auxiliary motors. Okay, and this is derived. This supply is derived from the main motor. So that is why this is called cascading of the two motors. Okay, so if the torque produced by both act in the same directions, then cascading is called cumulative cascading or additive cascading. And if torques are in opposite directions, then cascading is called a differential cascading. So this is actually the arrangement. Okay, this is the main motor. This is its rotor side. It is mounted on the same shaft. This is the slip-ring of the main motor. So this main motor is supplied from the three-phase supplies, and from the rotor, from the power is derived from the slip-ring, and it is given to the stator windings of the auxiliary motors. Okay, and auxiliary motor may be a slip-ring type or say slip or squirrel cage motor also. So these slip-rings of the auxiliary motors are connected to the external rheostats. Okay, so actually if the in this process if the torque of the both motors are in the same direction, this is the cascading is cumulative, and if it is in opposite direction, this is differential cascading. Let us suppose the main motor is A and auxiliary motor B, and let's say PA is the number of poles of the main motor and PB is the number of poles of the auxiliary motor. Let's say the supply frequency is F, so then synchronous speed of the main motor, that is motor A, is equal to NS equal to 120 by P, and let's say N, actually the actual speed of the concatenated or cascade sets, then slip of the main motor or motor A, it is NSA minus N by NSA as per the definition of the slip, and this is the frequency of the rotor induced EMF of the main motor or motor A. Let's say we can write this frequency equal to the slip, the main motor or motor A slip into the supply frequency. So as from this relationship we know, that is the rotor frequency equal to the slip type S type time the supply frequency. So the supply of motor B, that is the auxiliary motor, is at frequency Fa, that is equal to Fb, the frequency supply frequency of the main auxiliary motor, motor B. So that is equal to the rotor induced EMF frequency of the motor A, that is the main motor. So synchronous speed of the auxiliary motor, that is motor B, equal to 120 Fp by Pb. And so if we write here, so Fb equal to Fa, if we put here, so it is 120 Fa by Pb. So let's put this Fa equal to Sa into F. So this equation becomes 120 Sa F by Pb. Now put the value of Sa equal to Nsa minus N by Nsa. So this equation converted to 120 into Nsa minus N whole into F by Pb into Nsa. So on no load, the speed of the motor B, that is the auxiliary motor, that is of course the say N is the speed of the concatenated set. It is almost equal to the synchronous speed NSB. So that is NSB, that is the speed, synchronous speed of the auxiliary motor equal to the speed of the set. So that is it is the speed of the rotor, and N is actually, as I told you, this is almost equal to NSB. So we can write N equal to this. So 120 NSA minus N into F by Pb into Nsa. So if you simplify it, so 120 F by Pb into, so divide this Nsa minus N by Nsa, so it will give you 1 minus N by Nsa. So it will say converted into 120 F by Pb into, now put the value of Nsa equal to 120 F by Pa. Okay. So this N equal to how much? So it will, if we simplify it, so it will be like this. So 120 F by Pb into 1 minus Npa by 120 F. Okay. So N, now by simplification of this, so N, the speed of the set on a cascaded set, so it will be 120 F by Pa plus Pb. Now, if by interchanging the two terminals of the auxiliary motor, that is motor B, the reversal of the direction of the rotating magnetic field of B is achieved. Okay, so then the set runs as a differentially cascaded set, and in such a case, an effective number of poles will be how much? So it will be just difference of the poles of the main motors and the auxiliary motor, that is Pa minus Pb. Okay, so and that is achieved. So by rotating the motor B or auxiliary motor in the reverse direction. So and that can be possible only by interchanging the two terminals of the motor B, the two terminals of the stator winding of the motor B, of course. So thus in cascade control, 4 different speeds are possible. How 4 different? Because with respect to, first one is with respect to the synchronous speed of the main motor independently, that is synchronous speed equal to 120 F by Pa, that is A is the main motor, and with respect to the synchronous speed of B, that is auxiliary motor independently with main motor. Main motor is disconnected and B is directly connected to the supply, and then in that case synchronous speed will be 120 F by Pb. Okay, so this synchronous speed for the main motor independently, this is synchronous speed for the auxiliary motor independently. Okay, and running the set as a either cumulative cascading or differential cascading. So when the running set as a cumulative cascaded, its speed will be 120 N equal to 120 F by Pa minus Pb, and for differential cascading, N equal to 120 F by Pa minus Pb. So these 4 possible set of speed can be derived from these cascade connections. But what are the disadvantages? Definitely there are some disadvantages because it requires 2 motors, which makes the set expensive, and definitely smooth speed control is not possible. Only 4 speeds are possible. Operation is complicated, and of course the starting torque is not sufficient to start the set. and set cannot be operated if the number of poles for both main motors and auxiliary motors are same. So these are the very different disadvantages or limitations of this cascade connection of type of speed control. Okay, so so this is all about this cascade connection by operating two motors in cascade or concatenation or in tandem operation mode. Okay, so we have discussed. This is the say connection diagram of the set. Okay, this is how the different speed can be achieved. So starting from the say say it is derived and how it is derived, it is shown and discussed, and how we are getting 4 different speeds that is independently running the main motor one speed, independently running the auxiliary motor another speed, running the set as cumulative cascading so another speed, and running the set as differential cascading another speed. And we have discussed the disadvantages of these two motors also. So it requires two motors which makes the set expensive, and smooth speed control is not possible, operation is complicated, and starting torque is not sufficient to start the set. So and set cannot be operated if P minus PB. So in today's class we have discussed that is the another two different method. In the last class we have discussed is the consequent pole method. By changing the stator pole we can change the speed, and today we have discussed the multiple stator winding methods and pole amplitude modulations method. And besides that we have discussed rotor rheostat control method, but we have at the same time we have discussed the difficulties or disadvantages of this rotor resistance control method, and now we have discussed the speed control by operating two motors in cascade modes, and here also we have discussed the disadvantages of this process. So actually this is about the type of speed control we have discussed. Now in the next class we'll discuss by injecting an EMF in the rotor circuit. So once again I am telling you, so for this methodology we have mostly followed the books, textbook as P.S. Bhimla electrical machinery, or say Nagrat and Kothari electrical machines. Okay, Fitzgerald and Kingsley as a reference books, MG say as a reference books. Also we have conducted say discussed or taken help of electrical machines by Asfaq Hussain. There are not many good books I have given in your say bibliography or reference books number, and if you find any difficulties, I told you that you may contact me. You may over say phone or mail or WhatsApp, whatever the methods you find suitable for you, and say by this we can again clear or say any type of difficulties if we have, so we can discuss definitely. So in the next class we'll say discuss speed control by injecting EMF in the rotor circuits. Here we'll discuss particularly two methods, camera systems and Sebius systems. How these systems work, that will be discussed, and then also we will discuss the advantages and disadvantages of these two systems, cameras and Sebius systems. Also we'll try to discuss the slipper recovery STIM, that is static camera drive, and static Servius drive. Okay,